grew up in Newcastle, though. So, definitely Australia. So I work on a number of different things at Joyent, like a lot of it operating systems engineering, but also we have a number of different large distributed pieces of software written in Node.js, one of which is called Smart Data Center, which is our cloud orchestration stack, which controls all of the servers in our public cloud and also in the private cloud software that we sell to other companies to run their own clouds. And more recently, the Manta object storage and compute system. So I'll talk about those a bit later. But first up, I just wanted to give like a quick whirlwind tour of some of the debugging tools that we've written and used in the last couple of years as we stand up Node.js in production. It turns out, as with any new and upcoming programming system, there are a number of unique challenges, particularly around some of the things about dynamic languages, which make them good for programming in, but also harder to debug, often, particularly like a lot of the asynchrony in JavaScript. So, I mean, a quick show of hands would be good. So how many people have stood up a Node.js application in production with 100 users, 1,000 users, 10,000 users? No. I don't know, we have some number of users. I'm not sure exactly how many. But, all right, so I guess I'll dive in. Also, actually, has anyone used the Joyent public cloud as well? Fair enough. We'll try very hard. So, one of the things that you traditionally haven't gotten from like dynamic language environments like Ruby or Python or Perl is this idea of post-mortem debuggability, where the system is great up until it isn't, and then when it isn't, it often goes flying spectacularly off the rails. And it would have been really nice to have had 2 or 3 weeks to inspect the state of the system at the point where it flew off the rails. So in very traditional, like C-based systems, you had these things called core dumps, which were basically just a dump of all of the memory in the process at the time when it hit some kind of abort condition, and that's saved to disk by the operating system. The program's not involved, and that core file can then be loaded up in a debugger at a later time. This is really good because it means that you can take an application which is broken, and you can restart it immediately after aborting. Saving a core dump, and you can then, not affecting the production system. The production system comes back online very quickly because you've restarted it. But you can go back later and you can look in the like, it's kind of like an autopsy essentially on the process state. You can also induce a core dump of a running process without stopping or interrupting the process. We have a facility on the operating system that we developed at Joyent called Smart OS, which is based on the open source heritage of Solaris through the Illumos project. Called G-Core, which requests that the operating system take a core dump of a running process. So this can be really good for, in the instance that you have, I'm sure that most people have written a Node.js server that has gone off into limbo in some kind of CPU-bound infinite loop, and it's very hard to figure out, unless you turned on a lot of debugging and logging and stuff up front, which is not great production use, then it's very hard to figure out where that program was when it went south. So we have, as by way of example here, very, very simple web server. It has one root handler in it. You guys can read that? Cool. All that it really does is accept one input parameter, input num, and if the input num is 10, then we loop forever, and otherwise we just return 42. So, it's a trivial example that we will now run. With Clulow, and you can see that it's okay with 15, 14 is okay as well, but if we give it 10, then the program hangs, and we're going to look at, oh goodness, it seems to be consuming a lot of CPU, I'm not sure what it's doing, maybe we stop that and try a different request. Oh god, it's gone away forever, that's not very good. Panicking, production down. Operator gets on the box and says, alright, I'm going to save a core dump of this process, and then I'm going to kill it and restart it. So it is back to service requests. And while it's doing that, we can go and look at this core dump. So a core dump, traditionally, you would look in these and you would get what's known as a C stack trace. Now, JavaScript is a dynamic language, you get a bunch of memory addresses. Not very helpful. So one of the engineers at Joyent, David Pacheco, wrote a fantastic piece of software which can essentially demangle the V8 stack frames in a core dump. So we can go and this, you can now see that at the time the process died, or was, at the time we took the core dump, this was the JavaScript stack that was being processed. So see if we go back and look at the code. There is the route handle route 0. That appears in the stack, and then it was calling into make response, which for some reason is infinite looping. I mean, in this case, it's a very simple example, but in production code, like we had an instance of a piece of production code that was doing a binary search, and the min and the max value, if they were the same, then it would loop forever. And this happened almost never. I think it happened twice in production over 2 years. And we got a core dump the second time, and with these tools we were able to solve the problem, which was good news. And there are a lot of blog posts about some of this stuff, which I'll talk about briefly at the end. But the really interesting stuff is you can look at this stack frame, and we can say, tell me more about it. And the arguments that it was called with are available to you. So we can see that it has a request, a response, and an X function pointer. We can grab that, and we can print it out. So we can see all the stuff that would be in the object, time. And one of the interesting things in this case is the params part. We can see that the input number was 10, which came through the web request. This is the web request we were dealing when the process went away. And we can go back and read the code and figure out what went wrong and say, input number is 10, we look forever, that's not very good, we should fix that. So I mean, that's a good example of just the flow that you get from using these tools. And core dumps are a very useful tool for getting to the bottom of issues like this that don't happen very often, but often when they happen in production, and it's very bad. It's very hard otherwise without this to figure out what's going on. So that is MDB, which is only available on SmartOS at this point. There are similar debugging tools for other platforms potentially, but MDB has pretty great first-class V8 support. So it's one of the things that you can get access to on some of the Joyent bits that we work on. So another tool that we have available is dtrace, which is, I don't know how many people have heard about dtrace. That's more than 0, that's good. So dtrace is a production-safe dynamic instrumentation technology. What that means in practice is it kind of does things a little bit like a debugger in that it can put probes into your code, and you can fire events that happen on those probes, and it can give you tracing output. So you can do things like you can trace when your process reads files or writes stuff to the network, any number of other different system call actions. You can trace when those things happen. You can trace information about them, like what content was written. You can do things like aggregate on the size of the data that's coming across the network and get rates of flows. And particularly with Node, what's very interesting is that there's this facility called USDT probes, which is user static defined tracing probes, which are points in your application, which when not enabled have essentially no probe effect. But you can then, while your application is running in production, go and run dtrace alongside and activate these probes for as long as it takes to answer the question that you have about what's happening in your application. So as a brief example, there is a framework that we use a lot of Joyent for doing REST service called Restify, and server's running, and this script activates a little bit of D, which will grab out of the Restify has a couple of built-in dtrace probe points for the start of route handling and for the end of route handling. And so we can grab things like the method and the URL, and for each different request, there is a unique request ID, so we can then track the timestamp that was the start of that request. And then on the route done probe, we can track, we can print out the difference between the timestamp at the end and the timestamp at the front. So we can figure out, over time how long each request takes. So if we go and do a call there, you can see that we're able to get out of another process that's running. There was a get for a particular URL. The status was 200 at the end of the request. It's request ID 1, and it took 4 milliseconds roughly. And you can do them in a loop. So you can see each one there, and you can do things like dtrace has very powerful in-kernel aggregations of data. So you can say things like, let's aggregate on the method type, and then we will count the number of each type of method that occurs. And every 1 second, we will print out that aggregation. In addition to all of the different tracing, you can also do things like, if I had posts as well, you would see get and post and head and all these different methods. And that's just to count the number that occurred. You can do things like aggregate on the latency, draw distributions of plots of different latency and stuff that you can add. It's good for measuring the performance of, if you want to monitor how long particular routes on your server are taking and figure out that, actually, when I post the login form, that always seems to take 20 seconds, but when I post update some CRUD record, that only takes 2 seconds, and you can start to break down and ask and answer questions like this in production without really noticeably slowing down the application at all, and only for the length of time that you want to do the instrumentation, without having to restart the application, and it's essentially entirely production safe. There shouldn't be anything, certainly there isn't anything we're aware of that you can do with dtrace, and it's been around for 10 years now, that will break the application, which is a very, very important thing for doing these production apps. One of the other exciting things you can do is you can get profiling stack traces out of and do this thing that Brendan Gregg, another Australian who works at Joyent, invented called flame graphs that are essentially like a way to aggregate profiling data so you can figure out where your application is spending its time. So this is an application with a really trivial implementation of Fibonacci numbers, factorials, and then we just do in a tight set immediate loop. It's just as fast as possible, basically. We do 60 of the Fibonacci calculations and 60 of the factorial calculations. It turns out they both take a different amount of CPU time. So if we run that, see that it is busy on the CPU. And then if we generate a stack set process. So this will go away for 10 seconds and do some descript stuff. And there's a blog post that I can point you all out later that talks much more detail about all of this stuff for us. Just a tour of what's possible, I guess. So that produces a pretty picture like this. So what this is if you imagine a stack trace, the first function calls at the bottom, and as it calls functions, they go at the top. So this part is the amount of samples that was the factorial calculation. And so the common elements of the stack are drawn together. So the application is running, start running a bunch of things, and then we get into process immediate, which is every time that we run set immediate, we then process the thing that we scheduled in set immediate. So most of the time, process immediate is running, which is fine. And then thing duo is the function that we were calling that called the other things. So you hover over, you can see that 99% of the time that function was running because it was hot on CPU, it was doing a bunch of stuff. And then we can see that do factorial is running 36% of the time, and then the other 63% of the time is the Fibonacci stuff. So even though we're running them the same amount of times, one of them was more compute intensive, it took longer to run, essentially, than the other one. And then you see over here that there are a few crazy things going up here. Marcel and I were trying to figure out what that was earlier. It turns out it's garbage collection because we seem to allocate a bunch of memory in the Fibonacci routine and then throw it away immediately. But so if you can picture an application which does much more complicated things, like if you do a lot of JSON parsing, we found in some of our production apps that use a lot of JSON to communicate between two different nodes, like through REST APIs and stuff. That if you're doing a lot of different messages, then most of your time can be end up spent doing JSON parsing and like stringify and parse essentially, and that will definitely show up as a stack in the flame graph. And it will show up as like a thick mountain, and you can then go and figure out if you need to be doing that much JSON, or it could be that you're doing a really inefficient sort or something like that. This is a really good way when you have an application that is filling up the CPU that you're on, that you have available to you, and you need to figure out why it's doing that. Then this technique basically just periodically takes stack traces of the running application every, I think in this case I was using 397 Hz, which is relatively prime so as not to line up. Let's say if you did something every 100 Hz or every 10 Hz, you don't want to sample at for aliasing purposes, you don't want to sample at the same rate necessarily as in lockstep with periodic tasks. So you do something like 97 Hz or 397 Hz to try and sample around the periodic task that you're running. You get this, you get a lot of stacks, and then they just crunch down, and essentially each stack trace is vertically in the thing. So we do this a lot for for figuring out performance problems in different bits of applications. It's pretty good tooling. So with the probes, like the rectify probes I was talking about, you can add your own probes. You can give them names. You can spit out arguments. Spit out integers or strings. The common pattern that we use at Joyent is these days we have a logging infrastructure called Bunyan. Bunyan is a JSON formatted logging infrastructure, which is really powerful. It does the usual info and debug level type stuff, but it also, like the format that it produces is line separated JSON, so each line in the log file is a full JSON object. Which includes a number of standard fields like timestamps and the log level, host name, the name of the application, things like that, plus whatever fields that you put in. So we tend to write like auditing level information, which we usually write at info level into log files. So like for web server components, we'll tend to log requests as info level stuff. There's a bunch of extra information that would be useful to have when we're trying to fix a problem, but we don't want to have to restart the application to kick it up to debug level logging and then have the increased overhead of writing those logs to disk that debug level logging tends to produce. So Bunyan makes use of this dtrace facility, and even when you're not logging debug logs to disk, the potential to log them is available because there is a dtrace probe that will fire if it's enabled, which spits out the contents of what would have been written to the debug log. So to show that in practice, we have a sample application. So this application just generates a bunch of random numbers, and then attempts to, like random numbers tend to be uniformly distributed, so it induces a few outliers as well. So I log a warning log to the console for anything that's above 16,000, which we would consider an outlier in this application. You might do that for anything with a latency above a certain thing, like meeting some business requirement or SLA. And then for every single random number that we generate, we log a debug level message. So if I run that, you see that there are a few log messages that come straight out of the console, not very human readable. So we store the log files in JSON format so that we can go back and process them easily with log processing tools later on. JSON formatted log files are particularly great because you can add fields to them without breaking all of your existing regexes. And, like the traditional problem with Apache style logs is that you tend to have, in order to make them easy to read, they have a bunch of different separated characters, and then you have this really complicated regular expression which breaks as soon as you try to add more fields. So we've done away with all that, and we just throw out JSON blobs with timestamps and stuff in them, and then you add fields, and then you can use the Bunyan command line tool to print them out however you like. There are a number of different templates that come out. You can see these are the warnings. every time we get a number over 16,000, that happens. And then I have and then the Bunyan monoline tool also has a mode where it does the dtrace stuff for you, so you don't have to. It's pretty easy. And then point it at the process, and it tells you all of the things that were coming out of that. Like it enables debug logging essentially, like, and spits it out on the console. So, and dtrace has a lot of back pressure safety features in it, so you can't tax the system to the point of making it unresponsive. So like whereas traditional debug logging, you would start writing to the disk a lot more, and you would eventually run out the I/O capacity on the box, and then that makes all the problems you're trying to solve worse. So rather than do that, you just have this dtrace probe thing, which uses the spare cycles on the machine essentially to spit them out on the screen or to a file if you wish. But and then you get out of that is the ability to if there are too many log events, then they just get dropped. They just get dropped as events, which is good. It's what you want when you're just trying to inspect the system without making it worse. And Bunyan lets you do a lot of things like filtering on the fields in the log messages. It's really easy because it's all JSON. You can do things. But also, the other thing too is because they're just dtrace probes, you can also write regular D. So this is looking at the Bunyan log debug probes that fire. They're called log debug. Anything that when you call the debug method on a Bunyan logging instance, that will spit out one argument, which just happens to be the JSON formatted string that you would have written to the log file. And then recently, like in the last 6 months, I added to dtrace in the ability to parse in the kernel so that we can aggregate on particular fields of these messages. So like I'm going to pull out the size here out of the JSON blob that comes out, and then we're going to do what's called a linear quantize on that, which puts the value of the size, which we believe to be hopefully linearly distributed plus a few outliers, into buckets and draws a graph. And then every 3 seconds we're going to print out the date and the graph. So that. So that is. So we are actually firing 68,000 of these debug log probes every second right now in the VM that's running very hot on my laptop. And you see that they are roughly normally distributed between the 1 and 12,000 that we're expecting, plus a few outliers down to about 16,000. And then you see that there was one 16,000, so that would have been a warn. So the condition that we set earlier. And you can do aggregations like this linearly or power of 2 bucketing or like part log, part linear. And it's really good for, particularly for when you have like a system that's doing like 100,000 web requests a second, it can be really hard to like make sense of like, are they all slow or is it just one that's slow every now and then? And so if you do this, if you can imagine you took the input to this bucketing was actually how long a web request took, and most of them could be like 100 milliseconds, but you'll see every now and then maybe one of them was 2 seconds and then one of them was 3 seconds. So those are like statistical outliers. And doing distribution plots like this makes it really easy to see that sort of stuff. Because the dtrace probe overhead is so low, particularly when it's off, you can have this and you can turn it on in production when you feel like there's an issue, and you can turn it off again straight away. So it's and these tools are pretty easy to use, and there's a lot of documentation. And we put out blog posts periodically about how to do stuff like this, with particularly around restifying, which we use a lot internally. And I mean, like all of this stuff is like the Node Bunyan is in NPM and it's open source, and like the Node stack viz is Dave's that generates those flame graphs. It's open source available as well. And then there's Node dtrace provider, which is written by a guy in the community, which is really fantastic. Which just lets you you just create an object with a probe name, and then you just call fire on that object, and it will, if the dtrace stuff is enabled, it will do that. Otherwise, it will do nothing, and essentially no overheading gets jittered out, which is really good. So that brings us, I guess, to Manta, which is the new thing that we've been building, which is one of the reasons we've been running around building debugging tools. Manta is a really big, complicated distributed system. It's complicated sort of underneath, so that the interface that it can present to people is very, very simple and easy to use. It is both an object storage service and a compute service, and it is a fusion of those two things. So you can put, essentially, I mean, we call them objects, but they're essentially like files. You can put files into this thing through either directly like HTTP put calls, or we have like a CLI, which is pretty easy to use, like runs on Macs and Linux boxes and some iOS machines. It's written in Node.js and it's open source, so it's a good set of examples of how to use this stuff. And it's all built on a lower level Node module, which is like the SDK for doing this stuff. So you put it on, like, let's say you put 1,000 images up into this service, and then you can fetch them out again, like through regular HTTP requests, or you can do the thing which is really unique to the system, which is you can run any Unix software that you want on the same machines that the data is stored on. So by default, we store 2 copies of your data on different servers dispersed throughout the Manta cloud. And then when you request the running of a job on particular pieces of data that you uploaded, we farm it out to those machines. We run it, and then you're only billed for the number of seconds that it takes to run that job. So it's much, like it's really good for very low duty cycle stuff, or periodic jobs where you don't want to spin up a bunch of infrastructure all the time. You just want to run like a daily report across a few log files that might take 2 minutes to run. Or if you want to resize like 10,000 images, create new thumbnails, or if you want to do video transcoding, if you want to do all kinds of things. Manta is really good for that. It has pretty first-class support for Node.js, and we write a lot of. Most of Manta is written in Node.js, and we've used a lot of the Manta primitives for the log analysis parts of that system as well. So when we rotate web server logs and access logs and stuff, we rotate them, we put them up into Manta, and then we can run analysis jobs across them to figure out usage, and we use that for billing as well. We bill on downloads, I think. Uploads are free, we bill on downloads, so we use the web request logs to bill on that sort of stuff. And then compute jobs get logged as well, and then you get reports out of those that are just put in as JSON blobs in the thing. You can just get them out. So I'll show briefly the CLI. So the CLI that you get is, and again, the Node Manta toolkit is available on GitHub as well, and is written entirely in Node. You get the regular Unix tools like ls or MLS, technically for Manta, which goes and does, looks at all the files that I have up, and you can use name files as like regular Unix paths, and they're just regular files essentially. And, you can submit jobs to the system. I wanted to run a word count on that one. Essentially works with the map reduce sort of model. You run a map. So that will, mjob create and accepts a list of keys, or object names essentially from the store. I've given it just one to run this job. It will go on now and it will find the machine, that thing,